All right, so now we move on to lesson one of Unit A, and it's introducing the physics that we're going to be talking about, plus talking a little bit about average speed and speed calculations. So, jumping right into it, we deal with a little bit of the introduction. During this semester, what we're going to do is look at a lot of Newton's ideas. And Newton is considered the father of classical physics. And his three laws actually give us some powerful tools in terms of how we can analyze problems through kinematics, dynamics, and throughout the rest of the semester. And we can really say, okay, when do we have Newton's first law and what does that mean? When do we have Newton's second law? What does that mean? And lastly, when do we have Newton's third law and what does that mean? And it's going to help provide kind of an instruction set of these are the ways we can approach problems and these are the ways we can easily analyze problems so that we can solve them correctly. Now, on top of Newton's ideas throughout the semester, the big thing that we really want to highlight here is that we're learning classical mechanics or the classical physics. And so we can't move on to physics 30 until we have a really strong grasp of the physics 20 concepts. And it's because it's so pivotal for when you move on to that next level, you need to have these foundational skills of how do we study motion? How do we study forces on each other? And then how do we study forces applied? And furthermore, then how do we analyze waves and wave properties, which is way later in the semester. But we want to look at this and say we are setting the foundation so that we can move from larger scale problems into small scale size problems, like things like fields, magnetism, particle movement, all that stuff that comes later down the road. But for now, we're going to deal with a lot of the classical mechanics or classical physics. All right. Now, in this course, we're going to look at three major areas. The first major area is we're going to look at motion. And motion is what we call kinematics, or that Unit A, as I'm going to call it, Unit A. And this is saying if we want to deal with problems that are around acceleration, time, distance, speeds, velocities, displacements, all that other good stuff, we're going to study that in Unit A, and it's all going to be put together around lesson 9 and 10 when we start talking about projectile motion. That's when all of this unit gets kind of pieced together. But until then, we're going to be slowly building up these skills of the study of motion. The next one is going to be forces. And forces gets introduced in Unit B and then continues on throughout the rest of the semester. So I'm going to consider this to be Unit B/C. It could even honestly be Unit D, but mainly we start introducing the big conceptual pieces around forces in Unit B and then going on to Unit C. And then lastly, we talk about energetics. Now, energetics includes things like potential energy, it includes kinetic energy, and it also includes the interaction of forces and motion within those equations, or within those systems, I should say. And so realistically, I could say Unit A, B, C, D, but mainly we see this appear in C/D, where we really break apart how energy is involved, or more importantly, work, energy, and power are all related to motion and forces. And so realistically, by the end of this semester, if you can have a strong grasp on each of these three main areas of classical physics, you're going to do just fine at the next level, and you'll have a really solid foundation going forward throughout your studies of physics. Now, one thing we really want to key in on is the two types of motion, and this is huge this semester. The two types of motions that we're going to look at are uniform motion, which I often denote as UM in class. So if you ever see me write UM, that's referring to uniform motion. And there's two specific requirements that make this happen. We have to have a constant speed. Uniform implying that something is remaining uniform or consistent. So consistent speed is that first piece. And then the second piece that makes this uniform is constant direction. Constant direction is that other big one. Now, if we do not have one of these following requirements, then this automatically becomes non-uniform motion, or that there's acceleration involved. So I like to denote that acceleration is not equal to 0 when we have non-uniform motion, or NUM, num. Now, a prime example when I think about things that may look like uniform motion but are actually non-uniform motion is things like circular motion. And we discussed this in class a little bit, and I'm going to draw it above. If I draw a circle that you're going to see in Unit C, and we look at some sort of tennis ball being whirled around on this specific circle, then what we talked about in class is we said at each given moment, if I look at the tangent part of it, the tangent part at any given moment represents the given speed at that section. So I would say, hey, the speed is pointed tangent to the circle at that given point. And then if I was to study, let's say the ball is moving clockwise and the second position is here, I see that the speed is now facing downwards momentarily. Well, what does that mean? That means that we have non-uniform motion or accelerated motion, because the key requirement that is not met when we're looking at uniform circular motion like this in unit C is the constant direction. We definitely have constant speed. It's the same speed everywhere, but the direction is different, meaning it automatically becomes non-uniform motion. Now, obviously we'll get there. That's unit C, but I really want you to be aware that even when things seem like they might be uniform motion, unless they follow both of these key requirements, then it is considered non-uniform motion. All right, now a couple definitions. Distance. Purely distance is the amount of space or how far between 2 points. And this can be measured in a ton of different units. They provide meters, kilometers, centimeters. It could be anything, millimeters, miles, whatever we really want it to be. But it's just saying how far overall. What is the total magnitude of distance covered? Time basically says how long does it take to travel between 2 points. So realistically, time is related to uniform motion, non-uniform motion. It can be related to distance and displacement. But in the case of the average speed calculations we're going to do, we look at it and we say, how long does it take to cover a total amount of distance? And then lastly, speed is just defined as the rate in which an object is moving, or more specifically, based on our lesson 0 that we covered, it was the change in distance over any given unit of time. And the way I explained this in class is I said distance, which is our y-axis or our output, if we want to call it that. So you could say this is your y-axis. Your y-axis, or more importantly, your rise, for any given unit of time, which was our x-axis and primarily our x-axis. And then this is also symbolic of the run. So rise over run, distance over time gives us our speed calculation. Now on the next slide here, we see that put together in a formula. The only thing that's different from your formula on the formula sheet is we see speed average and velocity average. But for now, we're going to call it speed average equals the total distance or the total change in distance over the total change in time. One thing I really want us to look at too here is that we're going to consider these to be our standard units. So I really want you to highlight those in your notes and even star them next to it and be like, this is how we're going to answer the most of the questions. If they ever ask for time, a distance, a speed, it's always going to revolve around these. And very rarely, I mean, sometimes they may ask you for kilometers per hour or, other units, but for the most part, we're going to be dealing with meters per second, meters, or seconds. Those are like the most standard, most requested units, pretty standard for what we're going to be looking at. All right. Now, in terms of the first example here, pretty simple example, but we're going to put it all together. They say an object travels an object travels 510 kilometers in 4 hours. So first of all, they've given us a total distance and they've given us a total time. What was the average speed of the object in meters per second? Now that's a really critical thing. They gave us kilometers and hours, but they want it in meters per second. So what I'm going to do is I'm going to go speed average is equal to the total change in distance divided by the total change in time. That means that my velocity average, or not my velocity, but my speed average, is equal to 510 kilometers divided by the 4.00 hours. And now, to make sure I get a really specific answer here, or to make sure that I get a specific kilometers per hour, I'm just going to make sure I had this right in the calculator. Perfect. 127.5 kilometers per hour. Okay, now we got to remember this is not the final solution, so you do not want to consider this the final solution. I'll even write that here, not the final solution. We have to do more work with this. Here's what we have to do. We can do unit analysis, which I would highly recommend, is just the first couple times writing that through. Or what I could do is say, well, in order to take 127.5 kilometers per hour and move it into meters per second, what do I have to do? I have to multiply it by, I have to divide it by 3.6. And so I'm going to divide it by 3.6, which if you did the unit analysis, you would see that 3.6 is just the product of saying 1,000 over 3,600. This is going to give me the following value, 35.4 meters per second. Now, again, just like I said in lesson 0, it's really, really important that you start treating this as the fastest way to get to the solution. Unit analysis is great. I love it. I think it's great. It has good payoff. It is really applicable to all the other sciences. But what I would say is that if you can do that quick rule of divide by 3.6, multiply by 3.6 when appropriate, it's going to save you a lot of time, and it's going to make sure that you're putting the majority of your effort into the physics notation and the notation that is critical, like putting the formulas together and making sure all your units are there. That's the really important stuff for us. And then these minor conversions, if you want to do full unit analysis, great. But if you don't, and you're just making sure all the other physics concepts are there and all the important key critical information is there, perfect, excellent. All right, example 2, we got a bit of a more applied one here. This equation, or this example, revolves around 2 scenarios here, or 2 parts. An airplane is traveling 1,800 kilometers at a speed of 1,000 kilometers per hour. So right away, what I would do is I would say, this is my distance 1, this is my speed 1. It then encounters a headwind, which slows the plane. So there's a new speed here, V2, for the next 2,300 kilometers. That's distance 2. What was the plane's average speed? So here's what we're going to look at. If I write the formula for average speed, it's VAV is equal to the total distance divided by the total time. Well, hey, look, this piece we don't know. We don't know anything about the time yet. So what I'm going to do is I'm just going to box this away for a second and be like, hey, there's our original equation. Before we continue, what we need to do is we need to figure out how much time was spent in each of these given intervals. And so I'm going to go part number 1. We're going to go change in time is equal to change in the total distance divided by the given speed at whatever interval. Now, how did I get this? I simply multiplied the time up to the other side and divided the speed down. So if you need any work with that, I would definitely recommend just trying these on your own and manipulating these equations. But in Science 10, you got lots of exposure with this. Now it's about plugging the numbers. So I'm going to go change in time 1 is equal to the change in distance in 1 over the speed in 1. That's going to give me the following, 1,800 kilometers divided by the 1,000 kilometers per hour. And therefore, when I talk about a total time in that first interval, it was 1.8 hours. Okay, so that's my first piece. Now, what I need to do is do that same calculation, but instead for the time in the second piece. So that's change in the total distance for 2 over the speed of 2. Now, this is going to be equal to 2,300 kilometers, which was the total distance traveled in that second section, divided by, we have 850, which is that slower speed once it faces a headwind being it's going into the nose of the plane. And therefore, we say the total distance or total time, spent in that second interval is equal to 2.7058. Now, I'm holding on to as many decimals as possible just to make sure my final answer is as accurate as possible. So don't round until you get to the very end. All right, now that we have the total times in those 2 intervals, what we're going to do is we're going to go step number 2 is to put it all together so we can get an average speed. VAV is equal to the 2 distances together, so 1,800 kilometers, plus the other distance, which is 3,200 kilometers, divided by the total time for both of these. So 1.8 hours plus 2.7058 hours. Okay, when I do this calculation, I get a speed average of 910 kilometers per hour. Now, if you stopped there and you said, hey, this is my final answer, this is what I'm getting, I would be totally fine with that. And the reason is because they weren't specific on, do they want it in kilometers per hour? Do they want it in meters per second? If they did want it in meters per second, well, in the last lesson and this lesson, we've actually done a very simple conversion factor. If I have kilometers per hour and I want to move it into meters per second, all I do is take that number and just divide it by 3.6. When I divide it by 3.6, I get a speed average, which is equal to, and just to make sure this is completely accurate, 252 meters per second. Some of you may have got 253 as well, but that's totally fine. As long as it's within that plus minus one or of the ones place, you're totally fine there. So that's how we can get our speed average in kilometers per hour and in terms of meters per second. Now, again, which one's more common as an answer? Probably this one, meters per second, but you never know. They may just ask for it in kilometers per hour. So you can always be prepared for that. All right, we got one more problem to look at, and it's example 3. This one's pretty visual. On D2L, you're going to see that it has a pretty involved solution, but I'm going to really try to boil it down as simple as possible so that you can replicate these types of problems in a very meaningful way where you're actually analyzing it on a way that's a little bit more intuitive than just doing these page-long solutions where you're creating common ratios and substitutions and all this other stuff. We're going to boil it down a little bit more simple than this. Now, these problems are really nice. I really like these because they're good test questions. They're really applicable to your knowledge of the speed equations plus your knowledge of applied math in terms of, hey, if I give you a situation where there's multiple things happening, can you put them together to make a final solution? So these are good problems. All right, now what we're going to do is we're going to draw out a picture for this one because I think the best way to represent this is with the picture. Mike is chasing Bill on a school playground. At the particular instant in which we call time 0, Mike is 25 meters back of Bill. So what I'm going to do is I'm going to fill out Mike and Bill, and then I'm going to draw a line between them and label that this is a distance of 25 meters to start. All right. Mike can run at a constant speed of 60 meters per second. So the person that is trailing can run at a fast speed. And then Bill, who's slightly in front, runs still at a decent speed, but it's just slightly less. How far would Mike have to run to catch Bill? How far would Bill run, and how long after T0 or how long after that original positioning would they take to catch each other? So what I'm going to do is I'm going to write M and B together over here. I'm going to draw a line to them and say this is when they've caught each other. And so at some sort of time, which we don't know, the change in time we don't know, they will catch each other. Now, here's the easy way to think about this and the really logical approach to figuring out what is the total time it takes them to catch each other. Well, you're probably thinking, what is the distance they have to close in order to catch each other? And you would be right by saying it's 25 meters. In order to close the gap, they're going to have to shrink that 25 to being 0 so that they can be side by side. And so when we look at the equation, step number 1, what we're going to do is say the speed average is equal to the total distance traveled or total distance needing to be covered divided by the total time that would take. Well, total time is going to be equal to the change in distance divided by the velocity average. Well, more importantly, that's just saying what is the velocity required or what is the velocity that would allow them to catch each other. It's going to be the difference in their velocities. So 16.0 meters per second minus 13.0 meters per second. So the difference in their speeds. Now, to be more specific, we say the change in time or the time required to close this gap is equal to the 25 meters, 25.0 meters, divided by, I take the difference in their speeds, that's going to give me 3.0 meters per second. And what you would find is if you type this in, the time required for both of these two people to catch up to each other, or more specifically for Mike to catch up to Bill, is equal to 8.3 repeated seconds. So this is that first piece, or more importantly, the way that the question asked it, it's more like the last piece they asked for. How long after time 0 would it take? 8.3 seconds. Okay, now if we wanted to use significant digits as well, we would probably say that it would be 8.33, but because this isn't technically like the final solution, I'm just going to leave it as that. Now, step number 2, what we want to do is we want to figure out what is the total distance each of these people travel. Well, to figure that out, we're just going to use the speed equation, but isolate for D. If I look at that and isolate for D, the change in distance for Mike specifically, let's do Mike first, is going to be equal to the speed that Mike goes at multiplied by the time it takes him to travel to catch up to Bill. Therefore, this is going to be equal to the following. The speed of Mike is going to be equal to 16.0 meters per second multiplied by the time. I'm going to try to keep this to 3 decimal places, and I highly recommend you put in at least 3 or 4 decimals just to create accuracy. When you multiply this out, you're going to get that he has to travel 133 meters. Okay, so this is the distance for Mike, and I'm going to be very specific. The change in distance for Mike from the start. Okay, now we want to do the same thing for Bill. We go change in distance for Bill is equal to his speed multiplied by the time it takes for them to reach each other. Therefore, this is going to be equal to the slower speed, which is Bill's speed, multiplied by the time, and I'm going to use a very similar decimal place, so 3 threes because it's repeating, and therefore I get a distance by Bill when they catch each other we get 108 meters. Now, we can highlight all of these. There's Mike's distance, there's Bill's distance, there's the time, 8.3 seconds, or more importantly, now if we wanted to go back, we could realistically write it as the following, 8.33 seconds, just to be really accurate to the significant digits, and that would be our final solution. Now, I want you to logically just think about this for a second. When you're looking at these problems, they had to cover 25 meters, there was a difference in their speeds, and that difference in speeds is what allows Mike to catch up. And then additionally, what we can look at right at the end to confirm we got the right answer is if I take the distance of the longer person and subtract the distance of the not the shorter person, but the person moving at a slower speed, what you should notice is that the difference in these is equal to 25, which it is. 133 minus 108, we get 25. So that represents that difference that they were originally separated by, and that the distance covered has to be shorter for Bill than it does for Mike. All right, here's where we wrap up our lesson today. So that was the last question. Now I want you to go into the practice problems for lesson 1. There's lots of good practice problems on specifically calculating for time, speed, and overall average velocity, average speeds, and more importantly, just some of that fundamental stuff right at the start in terms of just using the basic speed equation. So get the practice, make sure you attempt them, do them all just to make sure you work towards that mastery, and we'll see you in lesson 2.